just a few schedule notes to start. So Lab 7 is due a week from tomorrow. Part of it involves semaphores, which we're just lecturing about today, and we'll cover in recitation on Friday, so it seems to be good to have a due date for a lab that uses semaphores to be next week. There's actually no built-in tests for Lab 7, so you get your points when you come to the checkoff, and the TA, you demonstrate to the TA what works, and he or she will give you the right number of points. And so in some ways, we can't really tell whether, quote, you finished Lab 7 by the deadline or only by the checkoff. And we're not too terribly worried about that, and you don't have to be either. There is a quiz a week from Friday, our last quiz in 6004. Just keep that in mind. And the final, absolutely, positively last deadline for 004 is 2 weeks from Thursday. At 5 p.m. So that's the end of classes, and that's when we are required by Institute rules to no longer accept any more submissions. So just keep that in mind. If you have any pending checkoffs that you need to take care of, or if you're working on the design project, keep that in mind as sort of the final moment in which you'll be able to submit improvements to your beta. Any questions about scheduling or timing or stuff like that? As usual, we'll be having a makeup the Monday following the quiz, and if your schedule suggests that maybe taking the makeup would be better for you, just let me know. Some people have asked, well, can I use my late days to extend things beyond the end of classes? And the answer, unfortunately, is no. The end of classes is the end of classes. Okay. Well, with scheduling out of the way, let's talk some about semaphores, which are I think, one of a fascinating and actually amazingly general purpose abstract data type that we use to allow us to basically communicate between processes. And so, it turns out that having concurrent processes, things that are conceptually running at the same time, is actually a very easy way, a very natural way to structure many sort of things that go on in an operating system, where you have something that produces information and something that consumes information, and the idea is to basically come up with a reliable way for transmitting information from the producer to the consumer. And this happens all the time. I mean, and in fact, these days it's quite natural to write most programs that have a user interface as multi-threaded programs where the events are handled in one thread and background processing is handled in another thread, and sometimes they need to communicate. So the techniques here we're showing here today is maybe perhaps one way to make sure that the communication happens correctly. There's actually, the reason I called it an abstract data type, there's actually many different ways to implement semaphores, and we'll talk about a few of those towards the end of lecture. But the real goal today is to understand the semantics of semaphores and how they get used, and then the implementation is usually given to you by the operating system or by the instruction set architecture. Okay, so the basic idea is that the producer is in a loop, generating something. In this case, we represent the something as a character to be sent to the consumer. So the producer's in a loop doing a bunch of computations and occasionally sends something to the consumer. And that just happens again and again and again. And the consumer is in a very similar loop, but its loop starts with receiving whatever the producer produced and then consuming it by taking it, saying, okay, I've got that character, and then presumably doing some computation, in this case YYY, that actually does something with that character. So that's sort of the underlying model that we have of what we want to have happen. And our goal today is not so much to focus on XXX and YYY, but is to focus on how to effectively get the send and receive to work completely reliably, with no possibilities of losing characters or anything like that. Okay, so this diagram here shows sort of those loops unrolled in time. If you sort of watch, you can see here's the different iterations of the loop. The subscript tells you which loop iteration we're talking about. And at the end of the first iteration of the loop, we send the first character, and then we start the second iteration of the loop, and we send the second character. And so this is, to think of this as the producer loop simply unrolled in time. And here's the consumer loop, again, unrolled in time. Receive, process, receive the second character, process it, so forth and so on. And what we're going to do is talk about what's the timing relationship that we need to enforce between these two programs, between when one, send can execute and when receive can execute, to guarantee correct operation. So we're going to introduce this rather strange notation, which is the precedes operator. And here we can say that A precedes B, happens before. So if we say, and we're going to use that sort of notion of precedes. We can formulate that as a well understood. We can look at the times at which things happen and talk about one time being before the other time. And what we're going to do is say, well, we're going to use those precedence relationships to describe the correct operating behavior. And so these both, I think, make somewhat intuitive sense. So this isn't like, oh my God, I don't understand what's happening. This is more, we're just introducing some notation to describe what we would naturally want for the semantics of our producer or consumer. Mainly that we don't want the consumer consuming anything that hasn't been produced yet. And so we ask for the ith send to precede the ith receive. And it's going to be up to us to figure out how to guarantee that's true. But you can sort of see from the semantics of the program, it wouldn't make a lot of sense for the consumer loop to be running ahead of the producer loop. The whole idea is that it's supposed to be consuming what the producer produces, character by character. In this particular case, if we imagine that there's only a single character buffer between the producer and the consumer, we also don't want the producer to overproduce. We want to make sure that the producer doesn't produce the second character before the consumer has consumed the first character. And now, almost immediately, we'll relax that constraint. But typically, there's something between the producer and the consumer that's getting information, that's holding the information as it's being transferred, and that something has a capacity that we can't exceed. So that's what the second relationship is here. What we've done here is just assume there's a single character buffer between the producer and consumer. So we have expressed that constraint, as that the ith receive has to precede the ith plus first send. And so we have this particular relationship we sort of show with solid arrows, and this relationship we show with dotted arrows. So with the additional constraints, that just sort of showing the relationship of when these computations can happen in time. Okay, so that's the basic setup, and we're going to spend some time thinking about introducing an abstract data type that lets us capture the precedence relationships, and then we'll talk about implementations of that data type. So the first thing we're going to do is notice that actually it never works very well if the producer and consumer have to be in lockstep. It's almost, why did you bother making them separate processes if after you run the producer, you have to run the consumer before you can run another loop with the producer? You might as well just put them in the same program. But it is quite natural to have a producer that produces a bunch of things and then spends some time thinking and produces a bunch more things. So there's this notion of the producer getting ahead of the consumer, but not too far ahead. And that turns out to be the sort of thing that occurs all the time in these producer-consumer problems. What we're going to introduce is a first in, first out buffer. So that just means that whatever order things are put into the buffer, when the consumer consumes them, they come out of the buffer in the same order that the producer put them into the buffer. So first in, first out just implies there's no rearranging of the ordering of the characters as they pass from producer to consumer. And in this case, we have n characters. And it's a little in this case, a circular buffer, which means it has, we sort of, as we produce things, we slowly fill up the buffer with characters, and you can see that sort of happening here. In this case, we've actually produced 3 characters. Now at this point, the ring buffer is full, the circular buffer is full, and the producer had better stop at this point. It better not go any farther produce anything more because there's no place to save anything. We need for the consumer to consume at least one thing. In this case, you can sort of see that it has a separate pointer, so the producer's pointer is on the top, and the consumer pointer is on the bottom here, and it's going, oh, okay, I'm going to, the next character I'm supposed to consume is this one, C0, so I do, and then that pointer keeps moving along. It doesn't seem to be moving very well. Okay, I'm sorry about the sort of shitty animation. But the idea is that they're both sort of stepping pointers to the buffer, and they can tell when there's something to either produce or consume. Does everybody sort of get the idea of how the circular buffer is working? The reason it's circular is that what we're going to be doing is reusing the first part of the buffer as soon as it's been consumed. So we use a fixed array, and conceptually we keep moving through the array, and then when we basically wrap around and start reusing the array from the beginning. That's where the circularity comes from. So this is a data structure that you just see an awful lot in almost anything that involves any sort of transmitting of characters or any sort of information from one place to another. There's typically some sort of ring buffer involved like this. Okay. Alrighty, so this is called the bounded buffer problem. We have a buffer that has a capacity n, and we have two pointers that are indices into that buffer. And here's the producer producing. It basically sticks a character into the buffer at the index indicated by the in index, the in pointer, and it bumps the in pointer modulo n. So it just steps through the array, and when it gets to the end of the array, it comes back to the beginning. And similarly for the consumer, it uses an out pointer to keep track of where it's reading, and so it takes something out of the buffer at the appropriate index and then bumps the out point, that pointer modulo n, and then we come back to the beginning. So we keep round and round we go. So here's our send and receive routines. These don't work because they don't enforce either precedence constraint. The producer can overproduce, and the consumer can quite clearly consume things that haven't been produced yet. There's no checking to see that the right thing has happened. So what we're going to now introduce is an abstract data type called semaphores, which will allow us to express the constraints that we want in a very elegant way. And we can use semaphores to solve all sorts of interesting concurrency problems between any two running processes, concurrent processes. This is a picture of Edsger Dijkstra, who was is a very famous computer scientist who he was instrumental in the formation of a lot of early, or I think of them as early, very interesting computer science concepts. And so semaphores was his general solution to this communicating parallel processes problem. And so we have a new abstract data type called semaphore. Implementation-wise, think of it as an integer. It's just a number. Okay. Now it's very tempting that now that I've told you that it's just an integer, for you to say, oh, well, I'll just treat it like an integer. But we all know, if you've had any experience with objects or abstract data types, we're not supposed to reach inside and fool with the representation. We're supposed to use particular methods for manipulating the values of the object. And the two methods that are associated with semaphores are wait and signal. Okay, and they have very simple semantics, which I'll tell you. But the only way we're supposed to do anything with a semaphore value, we can initialize it to some number, in this case k, and we can wait on the semaphore, and we can signal the semaphore. And so this is how this works. When you wait on a semaphore, what you're doing is the internal implementation of wait basically says, okay, I'm going to check the value of the semaphore. If it's non-zero, I will decrement it, or if it's positive, I will decrement it and return. So, however, if I look at it and I see that it's 0, I won't return to you. This is like one of these supervisor calls that doesn't finish until it can get somewhere. If you wait on a semaphore whose value is 0, you basically keep waiting until what? Well, that's where signal comes in. Another operation on the semaphore is the signal operation, which simply increments the value of the semaphore. Okay, and what will, if you think about it a little bit, wait and semaphore basically are wait and signal, I'm sorry, are very good at implementing the precedence constraints that we want. And there's lots of examples, so if it's not quite clear to you yet, it will be soon. But the idea is that by using wait and signal, we can cause the waits and signals to happen in a certain order. Okay, and some of that depends a little bit on what the initial value of the semaphore is. But everybody get the basic idea? Wait means you wait until the semaphore is non-zero, you decrement it, and then resume execution. If it's zero when you look at it, you basically, just conceptually you sit there and don't wait. You continue waiting until some other process executes a signal call, in which case the semaphore is incremented, and you go, aha, finally it's non-zero, I can decrement it and return. Good? Okay, and then signal is a very simple thing saying I'm signaling the semaphore, it increments the value, which presumably will enable some wait. So waits have the possibility of blocking, and signals have the side effect of not only incrementing the semaphore, but perhaps unblocking some other wait and some other process that's waiting for that value to be non-zero. Right, so from the signaler's point of view, I just incremented the semaphore, but that may enable some other wait now to succeed. Right, so there's a relationship between when signals happen and when waits unblock. Okay, and so this is designed to enforce the constraint. It depends what the initial value here is, but if I initialize the semaphore to k, some integer k, this will guarantee that the ith signal happens before the ith plus kth wait. Okay, or wait comes after. In other words, there's some number of waits that can happen as we busily decrement the semaphore down to k, and after that point, we need another signal before the next wait can happen. And if I set k to 1, only one wait can happen. If I set k to 0, no waits can happen until the first signal happens. So I have a lot of flexibility on establishing the precedence relationship between waits and signals depending on what the initial value of the semaphore is. So one of the things I've always enjoyed doing with the MIT libraries is to go look up the original papers. I mean, I don't know why I think that's sort of interesting, but I was a physics student. So when I first came here, I went off and I was fascinated by the idea that I could actually pull out the 1905 version of, Physical Review and look at the Einstein paper where he wrote about the photoelectric effect, right? And I said, wow, this is, I'm looking at it. This was the actual thing that arrived in the libraries in 1905, right? So I thought that was sort of fun. Well, you can do that with a lot of computer science papers too. So if you look up computer science papers on semaphores, what you'll discover is that for quite a while people use the names P for wait, and V, P and V for signal. And those have to do with Dijkstra's Dutch. So those have to do with and so those have to do with the Dutch words for wait and signal. Although when I went up to, I don't know if any of you worked with Franz Kaszek yet, but he's Dutch. I said, okay, Franz, quickly tell me what do P and V stand for. And he had no problem with P, but there seemed to be several interpretations of what V was actually representation for. Dijkstra doesn't really say in his papers, right? He doesn't actually give you the Dutch word they stand for. He just calls them P and V. So, anyway, more than you wanted to know, I'm sure. Okay, so here's the way this sort of works is we're going to use semaphores to manage a pool of resources. And so we're going to cast almost every problem of synchronization between communicating parallel processes as a problem of managing resources. So semaphore initialized to the value of k is managing a pool of k resources. And basically, when you need to use the resource, you wait on it. And if the wait returns, you have one of the k resources. It's been given to you. But because we've decremented the semaphore, it's not, that resource that you have is no longer available to be given to anybody else. And when you're done with the resource, you do a signal. Okay? Which basically means that you're done with it and you put it back into the pool so the semaphore gets incremented, so now it's available to other things. Now, there's no constraint that the wait and signal have to be in the same processes. which is how we're going to actually make a lot of things work. Alrighty, so this, an abstract conversation about an abstract data type. Let's see if we can be concrete. So the first thing I want to do is to deal with, the problem of the producer overproducing. I want to make sure the producer doesn't, I want to make sure, I don't want the consumer to consume characters that aren't there. I got ahead of myself. So the first constraint is I want to deal with I want to make sure that I don't consume any characters that haven't been produced yet. So I'm going to have a semaphore that represents the resource, which is the pool, or in this case, the buffer, of produced characters. Okay, we're allowed to produce up to n of them. Okay, but in this case, we're really trying to establish the precedence relationship that you can't consume something that the ith receive only happens after the ith send. And the way we're going to do that is we're going to have a semaphore whose initial value is 0 because we haven't produced any characters when the world starts. And after every time the producer produces a character, we're going to signal the fact that there's now a new character resource available. And every time the consumer wants to consume a character, it will wait on that same semaphore. And when that wait returns, we know there's at least one character available in the pool to be consumed, and so we consume it. So the wait decrements the count of the number of characters in the pool. Everybody get that? So we have a signal and a wait. A signal and a wait. And those could be in different processes, right? So semaphores represent basically a global resource that's available to all the processes. They sort of share, if you will, a big common namespace that every process can say, here's a semaphore, I want to deal with that. Okay, so does this work? And the answer is, well, yes, but it only solves the consuming problem of making sure that you only consume characters that have been produced. Okay, what it doesn't solve is the producer overproducing. Because there's nothing yet that prevents the producer from keep producing more and more and more characters, more than n characters. Okay, so the answer is that no, we haven't solved. We've implemented this constraint with that semaphore, with the signal and the wait, right? So I think of this as the sends do signals and the receives do waits, right? And so when I think of a semaphore, if I have a precedence relationship like this, I think of a signal at this end and a wait at this end. So whenever I see a signal on the wait, I'm thinking of both ends of the arrow, right? And so in this case, the arrow went from the ith send to the ith receive. So I have a signal at the end of the production cycle and a wait at the beginning of the consuming cycle. Okay. We still need this other relationship, okay, which in this case, because we have an n character FIFO, we want to make sure that we only send at most n more characters than have been received, and otherwise we need to wait. So how does that work? We need to sort of think about how do we get that other constraint in. Now you could sort of say, well, it looks like there should be a signal and a wait here too somehow. How does that work? So if we look at this, I'm going to introduce a new semaphore called space, and it's initialized to n. What resource is the space semaphore managing for us? So remember, this resource, this character semaphore was managing the pool of produced characters. What's being managed by that? What resource is being managed by the space semaphore? Yeah. Right, so we're talking about, if you will, holes in the buffer, spaces, empty spots, things that can be filled. And if you think a little bit about it, the producer produces characters that are consumed by the consumer. What does the consumer produce? When it reads a character, it produces a space in the buffer. Right, so we've basically recast everything as this producer-consumer problem. In this case, this guy over here is actually producing spaces in the buffer, and this guy is producing characters in the buffer. And we're going to use exactly the same mechanism, okay, to manage spaces and characters. And we're going to set things up so that the number of spaces in the buffer plus the number of characters in the buffer never exceeds n. And we're good to go. And so you can see here what we've done is whenever we free up a space in the buffer, we signal that the fact that there's now an additional space in the buffer, and the producer can't, the first thing it does is it waits until there's space in the buffer. Now, of course, when we start up the program, how many cycles of the production cycle can we run, of the production loop can we run, before the producer has to wait, assuming that no consumption is happening at all? How many times can we call wait on space before, yeah? N times, because it was initialized to n. Each n decrements it, and eventually that space semaphore will get down to 0, assuming that there's been no consumption. Now, of course, in real life, typically there's a little bit of consumption and a little bit of production, but whatever order the signals and waits happen in, we can now guarantee that I don't consume this signal and wait. These two guys here are making sure I don't consume characters that haven't been produced. And this wait and signal, this signal and wait here is the, if you will, the producer-consumer relationship in the other direction. That takes care of the arrow going from the blue to the tan, or whatever you want to call that. Okay, not really blue, it's cyan. Cyan to tan. Okay, going the other way, which is making sure that that we don't overproduce, that we have enough receives that have happened that there's a space in the buffer. So at this point you say, oh, this is actually, I mean, I thought this, when I first saw this, I said, this is actually pretty clever. You know, is to actually somehow think of a sort of a general purpose mechanism that reformulates every notion of any sort of synchronization between communicating parallel processes, concurrent processes, okay, as a general purpose abstract data type that sort of, you view everything as sort of a resource management problem, which is, it's actually, it's quite, you know, once I got it, I said, wow, I can use this Swiss Army knife to do almost anything I need to do in terms of making sure that the concurrency that's available to me obeys the rules I want to put out. In this case, having to do with not overflowing or underflowing the buffer. Okay, so now here's a different problem. Here we are, we're going to go to work for Bank of America here, and we're going to write some code. And the idea is that, you know, we have an account, and we're going to write the code that basically does a withdrawal, basically subtracts a withdrawal amount from an account. And, you know, sort of naively, we pick up the balance of the account, and we subtract the amount and write it back. I mean, that's, if you think of how the load and store operations work, that's sort of what we're expecting to happen. And so we sort of think that if two of us, Hans and Fritz here, walk up to the teller machine, and we're sort of expecting that, you know, the first guy does the decrement and the second guy does his decrement, and at the end, you know, we sort of imagine the code would sort of look like that. And you know, we collectively they both have 50, or collectively they have $100, and the account balance has been decremented by 100. Bank of America's happy, we're happy, everybody's happy. Okay. However, with our newfound notion that in fact we may have two debit code, you know, running in different processes. You know, there's two different ATMs. They're both sending messages to some big, huge cloud-based server, and the server is busily saying, okay, I'm going to process your decrement. I'm going to process your decrement. Depending on how things work and how the time sharing works and things like that, it may be, in fact, that the actual interleaving of the two pieces of code, okay, is done this way. Right, in which we start the process, you know, we start the debit, you know, the little 3 instruction sequence that does the debit for the first user, but we, you know, say, okay, wait, now it's time for this other process to run, and that process is dealing with the debit for the second user. And this particular interleaving is unfortunate because the first user has picked up the balance, and then the second user updates it, but the first user doesn't see the update because it's already got it. Thanks. You know, I'm just going to subtract 50 from it. And at the end of the day, you have $100 and the Bank of America has only debited the 6004 account by $50. Okay, so in the list of who's happy, we're probably pretty happy. We should all run over to the Bank of America machine this afternoon and see what we can do. You'll quickly discover the 004 account doesn't have much money in it. Previous semester's experiments, all that. What we're going to have to do, though, is we want to introduce the notion of, look, wait. Obviously, the bug here is that once I start manipulating the balance, I really don't want any other code to run. I want this notion of a transaction. I want to do a sequence of operations and have them happen as if they were atomic. Okay, now, atomic is a word that basically means once you start it, you finish it. No other interactions can be. That was sort of came from in the era in which atoms were sort of the smallest unit of matter. Of course, now we all know that atoms themselves can be broken into pieces and things like that. But quarkically doesn't seem quite the same come off the tongue quite so well. So we still call it an atomic transaction. So an atomic transaction is one that basically runs to completion with a guarantee that nobody else is going to get in the way. And I'll be more technical about what I mean by nobody else getting in the way. Okay, and the constraint that we want in this case is called mutual exclusion, and for many years they were called mutexes, the things that the type of semaphore we'll use to actually implement the notion that only one piece of code can be in the debit routine at a time. Okay, what we're going to do is, and nowadays we tend to call them locks. Okay, so we're going to add a semaphore. In this case, you can see we call it lock here. Sometimes we call it mutex for mutual exclusion. And this is very simple, okay? We're basically, now the resource we're managing is the permission to be running in the debit routine. So we basically wait for a lock, and once we have it, we now know that anybody else who's going to be in the debit routine would have to wait for the same lock, and since we have the lock, they can't get it. So they'll hang while we finished our transaction, finished the actual picking up the balance, subtracting the amount, and writing the balance back out. And then we signal that we're done, and which presumably will wake up anybody else who's been waiting. Everybody sort of get that? So this is sort of a mutual exclusion. You can think of this as a precedence relationship that either A precedes B or B precedes A, but they're never concurrent. They never happen at the same time. It's interesting to think a little bit about how you should actually write this code. So think about the code that I wrote that's on the screen here. And Bank of America say, boy, whenever there's a lot of withdrawals, things seem very, very slow. Now, why would that be? Why would it be if there's a zillion withdrawals? Everybody walks up to the teller machine at exactly 4 p.m. and says, withdraw. And some people say, I'm sitting here drumming my fingers. I don't know why it's taking so long. Why would it take so long if this was the code that the Bank of America server is running? Yeah. Right, so there's a certain notion of what granularity should we have for the lock. That means how much should we lock. In this case, this is one lock for the everybody who wants to do a debit anywhere in the world on the Bank of America account arrives at this routine and does a lock on it. And now we are sort of sitting there going, oh my God, I have to wait for my turn in a very long line. So that seems to be an unnecessary precedence constraint. Okay, what would be a more realistic constraint? If you were going to actually write this as a summer intern, you would say, well, this is sort of stupid. Why am I making everybody wait to subtract from the account? What is it you actually need to guarantee? Yeah. Each account would have its own lock. So all I'm trying to do is guarantee that two people aren't trying to debit from the same account. Okay. So sometimes the locks are so-called global locks like this, and sometimes they're actually locks on the account, or there are locks on a particular action in the account. And most languages like Java that support concurrency have the notion of having a lock on each object. So if each account was a separate Java object, you could actually have a synchronized object. That's a keyword you can use in Java. And then Java is going to be basically using semaphores to manage whenever people are trying to call the methods of that particular account. And so by simply applying the right keyword in Java, it will actually deal with all the low-level details of acquiring and releasing locks in the right way. But everybody gets sort of the big issue? One of the things that you'll notice in Python is that the built-in data types that you and I know about, like list and dictionaries, the mutable data types, the things that we can actually change the contents of, those are managed by a global Python lock. And so the way Python guarantees that if you have multiple threads that are sharing the Python data space and you're both manipulating the same list, the reason it guarantees you won't get yourself into trouble is that there's a global lock that gets shared. And so a mistake that people often make when writing multi-threaded Python code is they write it and it works great. The trouble is that what they don't realize is that every time they manipulate a list or a dictionary, there's a global lock. And so the multi-threadedness tends not to happen much because everyone's waiting for this global lock. So if you're going to write multi-threaded code in Python, anyone know what you do? How you get around the global lock? Well, you don't use lists and dictionaries. You use data types that people who run into this problem have created, like heaps and queues and things like that, where it in fact will those data types don't use the global lock, they actually have per object locks. In other words, people have provided you a separate pile of data types to use when you want to do multi-threaded data structures that are shared between multiple Python threads. But you don't want to use, and that's because of the global lock. Right, so the granularity of the locks turns out to have a lot to do with the performance of your concurrent system, so you have to sort of pay attention to that. Okay, so here we are. Let's see what happens now if we have multiple producers and multiple consumers. So that's the final step in our journey. Okay, and we sort of look at this and we say, fine, suppose I have two producers. Are there ways in which they might have an unfortunate interleaving? Okay, and the answer is yeah. Both people could be, basically trying to write into the same space. So here's another example, like the debit transaction. There's another example of the same problem, which is we need to make sure that the notion of writing into a particular index into the buffer is an atomic transaction. So we're going to basically solve the problem of producers interfering with each other and consumers interfering with each other, they're contending for the same space and or character, okay, is we're going to introduce, in this case, a semaphore called a lock semaphore, a mutual exclusion semaphore called mutex, which actually protects the actual buffer manipulation. Which means, so the idea with mutex is set to 1, meaning somebody can have it, but once one piece of code has it, no other piece of code can get it. Okay, we're going to go off and basically use that to protect the manipulation of the buffer. Now, this particular implementation also has unnecessary precedence constraints. In other words, this enforces some precedence constraints that aren't actually needed in order to guarantee that producers don't contend over spaces and consumers don't contend over characters. So what's the unnecessary constraint here? It has to do with sneezes, apparently. Yeah. Well, we have the same issue with the out variable that we had with the in variable, which is that when there's multiple consumers, they're contending for it. But the sort of thing you might occur to you is I'm using one mutex to guarantee two regions of mutual exclusion, when in fact the producers they can't interfere with each other and the consumers don't need to interfere with each other, but it's okay for producers and consumers to be concurrent. We actually solved that problem earlier. So in fact, if we were doing this, in the design review, it would be my job as the gimlet eye, old guy, the design reviewer, to look over my glasses and say, I'm sorry, Ms. or Mr. Intern, that's an unnecessary precedence constraint. Please fix your code. And you, of course, would say, oh, yes, I know what I would do. I would go back and build two locks, one for producers and one for consumers, and they would use the lock separately. Okay, so things seem peachy keen now. I'm sure you're all going, well, I'm glad we're done with that. semaphores. I now get semaphores. I'm ready to run off and finish Lab 7 now, thinking a little bit about how to actually make sure that the mouse clicks and the Pig Latin program can contend for the right to basically type out on the screen, so we're going to use a lock to guarantee that only one of those processes can type at any given time. With a little bit of shuffling of your feet to not try to get the lock too many times, you only get it once, you'll be in good shape. Okay, so the power of semaphores is that with these 3 semaphores, we've actually solved a lot of problems. We've solved the precedence relationships actually in both directions, and we've also solved the problem of the mutual exclusion, of making sure that we can create these atomic transactions. So this one primitive has been, we can sort of use it to implement all sorts of semantics about the concurrency, the allowed concurrency of programs. Okay, a little bit about the implementation. We just need a way of doing weight and signal in a way that guarantees that you can look at the semaphore and decrement it if it's non-zero, but you can't look at the semaphore and then if it's 0, decrement it, but have something happen in between when you looked and when you decremented, because somebody else may have snuck in and said, oh, look, it's non-zero and decrement. It'd be just like the debit transaction, right? So we need to basically ensure that we are able to execute the semantics of weight and signal, atomically, so other weights and signals don't interfere. The simplest approach for us is to make them supervisor calls. So the user mode programs are using semaphores. Once we enter the kernel, we know there can be no possible interruptions. So the idea that we're actually going to go off and read a variable and decrement it and write it back is something that we can guarantee that's uninterrupted because it's in kernel mode, and once we're in the kernel, we don't get any interrupts. So no other process is going to run in the middle, things like that. Okay, so here's the test for 0, here's the decrement. Different instructions, but we're guaranteed that if I execute this instruction, I'm sure to execute that instruction before any other process runs. Unless, of course, I've decided that it was 0, in which case I had better go to sleep and wait for that semaphore to wait for the signal to happen. Okay, so SVCs are one way. That's the way that shows up in the timing operating system. Okay, some hardware actually supports this test and clear instruction. And in fact, we could implement this on the beta if we wanted to. This notion that you go to a memory location, you pick up its value, whatever it is, and you set it to 0. At the same time, you do that as a single operation. Typically, the low-level memory system supports give me the contents and set it to 0 instruction. Of course, if you've read a 0, you know that think of this now as a binary semaphore. A semaphore whose value is either 0 or 1. And so you know what happens if you read a 0, you know you didn't get the semaphore. If you read a non-zero value, say, I've got it. And now I know everybody else will see a 0. And then when you're done, you just put a 1 back in that location. So the test and clear instruction is a hardware way of implementing binary semaphores, a very simple lock. Okay, and once you have a simple lock, you can use that to protect much more complicated code that involves, integer semaphores. One last fly in the ointment. That's a phrase my mom used for years. And, it wasn't, I went to Boy Scout camp and actually one day out of sheer boredom put some ointment on the table. And sure enough, a fly eventually got stuck in it. And so after that, I was able to say, a fly in the ointment is not a good thing. And I now appreciate, something I don't want to have happen. So the fly in the ointment in this case, fascinating personal history, I'm sure. Here's a transfer transaction where we're actually manipulating the balance of 2 accounts. Okay, so you think about what happens when each of these guys is running. They both, in this case, this guy's going to lock 0001 and then transfer and lock 0004 and transfer money this way. This guy's doing the opposite transaction. They don't know about each other. Okay, you look at this code, and there's something bad that happens. So I have a big picture here, deadlock. Can somebody tell me when I say deadlock happens, what the problem is I'm worried about? The scenario seems to involve sumo wrestlers. What's the scenario? Yeah. Right, so if you think about, here's this guy, the first thing he's going to do is lock 0001. And then let's say, okay, I'm going to go off and run somebody else for a while. And then this guy runs and he locks 0004. So far, okay, there's no problem. But what happens now is that if you have the 0001 lock and I have the 0004 lock, what's the issue? What's the next lock you want? You got the 0001. You want the 0004 lock. Why do I keep saying 000? I got so used to 00. These new curriculums are going to... We have another new curriculum hopefully coming our way. Goodness knows how many zeros that will have in the course numbers. Okay, so the idea is that you have 001, I have 004. You want 004, but you can never get it because I have it and I'm not letting it go because I'm waiting to get 001, which you have. So the deadlock happens when we're each holding a lock on something the other process wants. Oops. Bank of America says, nothing much seems to be happening anymore in our transfer system here. And the thing that's awkward is that we discover two processes that each conceptually could finish, but they're waiting for something the other process has. So that's called deadlock. Okay, and the famous example of problems with deadlock is the 5 dining philosophers. Okay, I don't know why it was 5. Here's 5. You can amuse yourself by trying to figure out who these guys are. They're all famous philosophers. And here's how the philosophers eat. They pick up their left chopstick, then they pick up their right chopstick, and then they eat. Okay, but this is a classic problem that might suffer from deadlock because what can happen? Okay, the turkeys are beginning to notice that maybe something's up. What can happen? Well, the problem is each of the philosophers can grab their left chopstick, but now their right chopstick is not available. There used to be a restaurant called the Spaghetti Emporium. I think it's, what's underneath, what's the restaurant now under the Galleria up in Harvard Square? John Harvard something? You guys don't go out? Anyway, when I was young, it was called the Spaghetti Emporium, all you can eat spaghetti, which you can imagine is a very bad idea in a college town. And I always thought I would go prime some waitress to go put one less fork on the table, and everybody's and everyone's waiting for the second implement because of course, if you know how to eat spaghetti, it requires 2 implements to help you do the twirling correctly, and watch to see what MIT students actually did. See if they actually went into deadlock. But does everybody appreciate the problem here? With this particular algorithm, we have what's called a circular wait. Right? The notion that everybody's grabbed one resource but isn't able to get the second resource. How can we solve this? Ask yourself, if you were saying, oh my God, I have to solve this in the next 3 minutes, what would you do? Okay, how would you solve this? Now there are some interesting changes to the algorithm. Yeah? Right, so one thing you can do is detect deadlock. Okay. And so so this notion of detection and recovery is that you calmly walk over to the table and grab the chopstick from one person and say, I'm sorry, I'll have to borrow this for a moment, and give it to the person next to them, and then that person eats. Once one person eats, then eventually all the deadlock is resolved. So you can detect it and recover. Okay, now it would be possible to run around looking for semaphores, looking for processes that are waiting for a lock, because they're stuck in that wait routine. And you can say, what are you waiting for? And then you can look for other processes that actually have that lock, okay, and see if they're waiting for something the first one had. So you can actually, with some amount of operating system code, detect these circular waits. Okay, another approach is avoidance. And what you do is you make a global ordering of the resources. You give them each an order, and every process everywhere, if there's a pool of resources that we might all be contending for in some order, we always acquire the locks in that particular order, in the order of the global ordering. So what we do is we number the chopsticks. We have something that says take the low chopstick and take the high chopstick, and we can guarantee there's never a deadlock now. You can sort of look at the little proof here. You know, the answer is somebody has the highest number of chopstick, and they would have had to have gotten a lower numbered chopstick in order to have gotten the higher numbered chopstick to get to step 2 of their algorithm. They've already gone through step 1, and so that person at least can eat. So everybody get the idea? Global ordering, and you can sort of think about that in the terms of accounts. What you can do is to basically just acquire a lock in the lower number account and a lock in the higher number account. So long that you're writing all the code everywhere, you can you can basically, with some thought, guarantee that you don't get deadlock. It's only when code is written separately where they may or not be obeying these sort of global constraints that deadlock is possible, and then you're up the creek. Okay, so it's a hard problem in general. There's a whole bunch of things going on, something called transactional memories that attempt to solve this very elegantly at the hardware level. You can read those papers. That's one of the hot new architectural topics. So have fun with that. Alrighty, that's it for semaphores. We'll see you recitation tomorrow and lecture on Thursday.